Okay, let's get started. Sorry about the delay. Okay. Okay, so welcome back. Hope everything's going all right. Before we got started, I just wanted to float an idea with you. I was talking with Darwen about the homeworks, and because there are more students, like I mentioned, there are more students in the class this year. And so we were just wondering about, whether we could do anything differently with the homeworks. And then this doesn't really address that, but one of the ideas that came up was I've sort of stressed the idea that the homeworks are not part of the assessment. The homeworks are part of the learning, right? The idea is that we assign you these questions so you can go away and you can actually try out some of the stuff we've spoken about in class. And that I think this is a very important way of, making sure that it's just a different way of understanding something, right? You can be told how to do something, but until you actually do it, you don't fully understand it, or so it seems. So that's the primary purpose of having the homeworks, is just so that you actually do this stuff, and so you get to see it from a different side. From that point of view, the idea of, that you do the homework and then we tell you whether you got it right or not is a little bit like, well, that doesn't quite seem consistent with that. So the idea was something I've heard of at different schools. The idea is that we would actually release the solutions to homeworks before the homeworks were due, at the same time as we release the homeworks. And then when you're actually working on them, you'd be able to finish a question, and you wouldn't have to wonder whether you'd got it right or not. You could immediately check the answer. And if you got it wrong, you could then go back and try and figure out how to get to the right answer. And I think this is sort of makes sense, right? It depends how you use it, right? It's very the way to do this would be, as long as everyone was sort of understood that the point of the homework is to think about the problem without knowing the answer, work through it, and then see if you got it right or not. Or see if so that you know that you're on track, rather than saying just sort of looking at the answer and working backwards. Then you don't learn so much, or at least you would learn something slightly different. So, but I just feel like, well, we're all here for the same reason, to learn this stuff. And so, giving you that tool and, relying on your responsible use of it seems like a good idea. Then the grading would be, we still grade the questions we still grade the homeworks. And again, the reason for grading them is just to give you an incentive, an extra little bit of reminder that, yeah, you're meant to be doing these questions. And by the way, if you don't, it's going to hurt your grade. But it's not like we're not trying to see if you got it right or not. We're just trying to see that you've actually done it. Basically, it's just checking off that you've actually put some work into it. So the solutions would probably not have a lot of detail how to get to the answer, and so that would be the part that you had to fill in. So that's the idea. If you have any comments or concerns about that, let me know, or send me an email, talk to me, or send an email to Darwen, or talk to Darwen. And then I'll let you know what happens about that. But that's the idea that we're playing with at the moment. It's also possible, just because that didn't really help, because if you're still grading the homework, it doesn't actually make any difference. The other idea was that we might not be grading all the questions in the homeworks. I know that somebody had mentioned that to me. I hadn't really thought about that, but it would certainly give us the opportunity to pay a little more attention to the questions that we did grade if we did go through that. Again, I'm not sure how that's going to work out. Any comments about that before we go on? Okay, but if that doesn't sit comfortably with you, then let me know. And I haven't decided yet. We haven't decided yet, but that's the proposal at the moment. I kind of like it because it's treating you more like grown-ups rather than like people who can't be trusted to know the answers. Okay. So last time we were talking about these sort of basic concepts in linear systems, in discrete time systems in the time domain. And so we talked about sequences as signals in discrete time, sequences of numbers, then operations we can do on them, basically adding them, scaling them, but also delaying them, and then maybe interpolation and decimation, but let's not worry about those. So these basic linear operations, basically scaling and adding, allow us to build this kind of a bunch of different structures where we can put down different delay elements, different scaling terms, and we can get systems out. And then we showed that there are a couple of properties that were very important to us. Linearity, which means that if you have a system, you feed in a signal, you get an output. You feed in a different signal, you get a different output. If you add the two inputs together, then the output is the sum of the two outputs you've got. So it's the idea of superposition or linearity. The other one was shift invariance or time invariance, which means if you put in a signal at time t, you get a certain output. If you delay it by a certain amount, but keep everything else the same, you get the same output. So and basically the idea was the arbitrary choice of where you choose to label t equals 0 doesn't affect the behavior of the system. It's basically a stationary system. It's the same whenever you actually start looking at it because there is no natural time 0. And so, you want to be able to start any time, label it 0, and have it behave the same. When we put both of those two properties, we had mathematical definitions. We showed that you can check that a particular system, a particular definition, obeys these by seeing if you can actually make the mathematical definitions work. That is, that the output from x0 and the output from x1 does give you the sum of the outputs from those two, etc. And so if we have both of those, we have linear shift invariant systems, and that's basically the highly restricted but still very useful class of systems that we're going to deal with in most of the class. There's also this idea of causality, which is basically the sort of the intuitive idea of causality. That's something that can exist, that you can build, and the constraint there is you don't have to know about the future. You don't have to have magical knowledge of what's going to happen in the future to actually build this thing. And so, formally, here's the definition. If you have two input sequences giving you two output sequences, if the input sequences are identical for all time up to some point, sometime step big N, then the output sequences will also be identical up to that big time point, up to that time point big N. Right, so it's just saying that this is the same as saying that the output at some time doesn't depend on the input any point in the future, because in this case, these sequences may differ arbitrarily after time big N, and so the outputs will presumably, in general, also not be the same. But as long as they're the same up to some point, then the outputs are going to have to be the same at that point as well. But that's what you get if you had a physical system where you could put inputs in and get an output out, and you were running it. And then obviously the fact that these inputs might change in the future, might diverge, they might become different, isn't known to the system at the time you're running it. So up until then, they have to give the same output. And so, well, we'll talk about that. We mentioned causal before when we were talking about right-sided sequences, but we'll see why in a second. So here's an example that illustrates causality. It's our moving average filter again. The y of n is the sum of x of n minus k for k equals 0 to n minus 1. So it's the 1 over m. It's the m point average of the last m input points, including the current one. So just, intuitively, according to the rough definition I gave, well, y of n only depends on x of n and x of n minus k for some positive k, so it only depends on current and previous values. So it does obey causality. And we could go through and test the mathematical definition, but we don't need to. We could think of another kind of moving average. We noticed when we looked at that plot of the moving average filter, somebody remarked that the output was delayed, right? And that was because it's a backward-looking index. It looks at the last m values, not just the current value. So it's got this kind of lag to it. We could try and just take that lag out by saying we're going to define a new thing, yc of n, which is y of n plus n minus 1 over 2. So we're going to take n, we're adding, so we're shifting it forwards in time. We're shifting it forwards in time. We're advancing it. We're looking n minus 1 on 2 points into the future. And that gives us an actual time, an estimate which is the best estimate of the current smoothed output. And so, we can define it here. It actually, if you work this through, it works out to be x of n and then sums of these pairs of x of n minus k and x of n plus k. So you take symmetric pairs of x around the middle point and add those into the average for m odd, I guess. But now we have this thing where we're looking at x of n plus k for positive k, which means we're trying to access x for n greater than the current value of n. So it's non-causal. It's only a little bit non-causal. We only need to look like 3 months into the future to get the 6-month moving average of current unemployment, but we don't know what it's going to be 3 months into the future, so we still can't do it. It's not something we could actually implement, so it's non-causal. Obviously, if we're looking at the unemployment in the 18th century or something, and we've got all those numbers, then we can implement it, no problem. But if we want to know the current unemployment, we can't do it. And of course, we can make it causal by delaying it, so that this n plus k then gets shifted back to time 0, but then we're just back with what we started with, right? So that's what we've got. We've got basically a delayed version of this non-causal sort of time-symmetric version. So sometimes you have these non-causal systems. If there's a finite amount of look ahead into the future, you can make them causal by delaying them. Sometimes you have something which, by definition, needs to know all of time all at once, and then you can't even make it causal by delaying it because it looks too far in the future. Okay, so now we're getting onto the kind of the central concepts of signal processing, really. Which I would argue is convolution. So before we get to convolution, let's just define the impulse response. And this is, again, a simple definition. We've already defined the impulse as the sequence here that's 0 everywhere except at n equals 0 when it's 1. And one of the things, if we have a discrete time system, we can feed in whatever we want. We could feed in this impulse. The output that we get when the input is the impulse is defined as the impulse response, okay? Fairly natural idea. And by convention, we use h of n as the impulse response. Now, what's kind of cool and not totally obvious is that if our system is linear shift invariant, then if we know the impulse response, if we just feed in this one simple sequence into the system and measure its response, then we've got a complete definition of that system. But the linearity and shift invariance means that that's all we only have to know the result of the output for this one elementary sequence, and we've got the ability to predict the output of the system for any input. So let's see how that works. But that's why the impulse response isn't just some arbitrary output for some whatever sequence. It's a very, very special output for this simplest of all possible sequences. Here's an example of calculating the impulse response. So here's our little kind of prototypical feed-forward discrete time system. We've got the input, we've got a couple of delays. We've got some gains here. When the moving average, they would all be equal to 1 over 3, but in general, they might be alpha 1, alpha 2, alpha 3. We sum them up to get the output. And if we think about running this machine, right, if we actually step through what happens, before time 0, everything's 0, so the output is 0. At time 0, we get a 1 coming in here, so we sum that up, we get an output of alpha 1. At time 1, we get a 0 coming in here, but the 1 percolates through this delay, so we get a 1 here, we get alpha 2 coming out. At time 2, the 1 shows up here, we get alpha 3 coming out, and then for times 3 and above, again, we've just got zeros everywhere, so the output is 0. So here's the input, here is the output, alpha 1, alpha 2, alpha 3, and 0 everywhere else. This is the impulse response, right? Because the input was an impulse, so the output is the impulse response. And now to say, well, this impulse response completely defines the system, it seems plausible because we've got this system which is defined by its structure and then 3 parameters. And here we have these 3 parameters sort of directly visible in the impulse response. So it doesn't seem unreasonable that it's captured enough information for us to be able to calculate the output of the system for any input. Okay, so here's how we tie all these things together, and it's basically through the concept of convolution. So if we have the impulse response of a linear shift invariant system, we put delta of n in, we get h of n out. Well, if it's a linear shift invariant system, then if we take any input and we delay it, then we get the same output, but delayed by the same amount. So if we have delta of n minus n0 going into the linear shift invariant system, then we get the impulse response also delayed by n0, h of n minus n0 coming out. Okay, if it's also linear, then we can take a couple of sequences like this. We can have deltas delayed by different amounts, and while we're at it, we can scale them by different constants. If we have this sum of different sequences coming in, then the output has to be the same sum of the outputs delayed by the same amounts and scaled by the same amounts. Right? That's the definition of linearity. But if we have some arbitrary sequence, not delta or even a couple of delayed deltas, but just arbitrary x of n, we can decompose this in terms of deltas by saying, well, this sequence which has got values at different times, it's sort of like we took a delta at time 0, a delta that has its non-zero value at time 0, and we scaled it by whatever the value the sequence took on at time 0. Okay, that gave us the 0th point, the n equals 0 point of x. And we also took another delta which has its non-zero value at when this argument is equal to 0, which is at n equal 1. So we took a delta at time 1, and we scaled it by a constant value, which happens to be the value of the sequence x at time 1. We have a delta that's 1 at time 2, and we scale it by a constant amount, which here we're taking as the value of x, the x sequence at time 2. So, this is this perverse way of expressing a sequence, but we're now expressing a sequence here as a set of, countably infinite number of delta sequences, very simple sequences, each one scaled by the actual value of x of n. And so obviously this is true, because if we think about what happens for some particular value of n, all of these deltas are going to be 0, except the one that's, n minus that amount, and then it'll be scaled by the appropriate value of x, so we'll get the right value of x out. So that's got to work. And so if we do this and we sort of break it down and put it into here, then what we're going to get out is the set of the impulse responses. Each one of when we put this sequence through the system, each one of these deltas is going to turn into an h with the same scaling constant and the same delay. But that's all. And then we'll get the output. So then, if x of n is the sum of these x of k's, which are now reading as constants, times delta of n minus k, the actual sequences, then by linearity and shift invariance, the output is this. We can just take each one of the terms in this sum, think of it, what happened, well, the delta turned into an h, and then we just keep the same scaling constant by linearity. So now we get a sum of these same scaling constants times each of these impulse responses. Right? And that's how we can use the impulse response to get the output of the system for any arbitrary input. We just run it through this expression. And this expression is so important and central that it has a special name, the convolution sum. It even has a special symbol. Right? So here we can write this as y of n is x of n convolved with h of n, where sometimes people use a star, sometimes people use star with a circle, but it's something like this. Now, this is a funny kind of expression because, when it was modulation, y of n is equal to x of n times h of n, then we could take a single value of n, and we could take the corresponding values of x and h, and do a point-wise calculation, and we get the value of y out. Here, it looks kind of the same, but actually, these things, this definition, this expression only works for entire sequences. Because in order to find y of m some particular value of n, in general, we need to know all of x and all of h. Because y of n, just if we hold n constant, we're still, in general, varying k over all possible values, which means we look at every single value of x and every single value of h. So this notation's a little bit tricky because it's not quite what it looks like. But a convolution, but it's still, if we read these as not statements about individual values for particular values of n, but as statements about entire sequences, so n is just taken as a dummy variable, a variable, then this is a statement about how we can combine these two sequences to generate an output. And indeed, this is the output you get for a system for a linear shift invariant system whose impulse response is h of n. Of course, you can only really define an impulse. Well, impulse response only makes sense for a linear shift invariant system. If you have a nonlinear system, then maybe the output depends on how large the impulse is. So there would be a value for for one, but it wouldn't tell you that much about for other values. And if you have shift invariant, then the impulse response would depend on when you put the impulse in, which again wouldn't be, so the single impulse at time 0 wouldn't be very helpful. But for linear shift invariant systems, h of n is a good definition, and this gives us the output. One thing we can notice right off the bat is that actually this expression is symmetric in x and h. That is, if we do a change of variable of this summation and define L as equal to n minus k, right? So then we get each term here. Well, the n minus k term just becomes L, and k is equal to, if we take k over here and L over here, then k is just equal to n minus L. So this k becomes n minus L. And then if we think about all values of k, well, if k goes from minus infinity to infinity, then L is going to go from infinity to minus infinity. But basically, we're going to have all possible values of L, just like we have all possible values of k. So we start the same summation here. And now we've got the same expression, but with, x and h kind of interchanged. So x convolved with h is the same as h convolved with x. That's pretty weird, right? That's what I'm saying. What I'm saying there is if I have a system with a particular impulse response and I put a signal in, I get the same output as if I use the impulse response as the input and then use whatever I was using before as an input as the impulse response. That they're interchangeable. They seem very different in the way we've defined them, but it turns out that the way they combine makes them indistinguishable afterwards. You can do it either way around. Okay. So just to restate that, for an LSI system, the output y of n is equal to the input x of n convolved with the impulse response h of n. And so that just, now that we've got this operation of convolution, well-defined mathematical operation, it means if I tell you I've got an LSI system and I tell you its impulse response, you can calculate its output for any input, which is functionally everything you could possibly want to know about the system. You know what it's going to do under any circumstances. So you've got a complete description of the system. You don't know how it's implemented, but you don't mind how it's implemented if all you're looking at is the black box and looking at the outputs. Other properties of convolution, we just saw that it doesn't matter which order you write these two sequences in, doesn't matter which one is called x and which one is called h in the sum. And so we call that it was commutative. And algebraically, we can just write the two operands in either order around the operator. It turns out it's also associative, which means if you have a sequence of these things, then it doesn't matter which order you combine them in. So if you have x convolved with h, convolved with y, it's the same answer as x convolved with h convolved with y. Again, this is, you see what I mean? So which summation do you resolve first? You can prove these things algebraically quite easily just by going back to the sum and working them through. It's distributive over addition, which means if we have h convolved with x plus y, then it's the same as h convolved with x plus h convolved with y. This sort of makes sense in terms of the linearity thing. That's kind of what we're saying, that the h convolved with x is the output from the system whose impulse response is h when the input is x. H convolved with y is the output when the input is y. So linearity said if we sum two signals into the input, then the output should be the sum of each signal individually, which is what we've got here, h convolved with x and h convolved with y. But sort of, algebraically it looks nice because now it begins to look like multiplication, right, because it distributes over addition. Okay. So, convolution is what linear shift invariant systems do. If you put a signal in to a system, what you get out is the convolution of the signal with the impulse response of that system. And that, in the limited world of linear shift invariant systems, that's basically the essence of what happens. That's what we're all about. So let's look at this. Again, I want to sort of get into the actual numbers think about what actually happens to give you some kind of extra insight into what's going on here. So here's the setup. We've got x of n, we've got some system which I'm now labeling with h of n because that describes the system. We've got the output, which is the convolution of those two. Here's the convolution sum written out. Y of n is sum over all values of k, x of k times h of n minus k. Or, because it's commutative, we could have written this out as h of k times x of n minus k. And so here are a couple of example sequences just so we can look at the numbers and see what's happening. Here's x of n. It's 0 until time 1. Then it takes on a value 3, 1, 2, minus 1. And after that, it's 0 again. So I'm just writing it here as this finite length sequence, but the understanding is it's 0 over other. I haven't defined it. And here's h of n. This is, the impulse response, what I get out of my system when I put a single blip in. And at time 0, I get 3, then it decays to 2, then it decays to 1, then it goes to 0. So it's sort of like, that we could build this with that system with the 2 delays and the 3 alphas, right? So this would be alpha 1 equal 3, alpha 2 equal 2, alpha 3 equal 1, and 0 everywhere else. It's just a couple of delays and a few waits, and that gives us that output. So let's look at what happens when we calculate the convolution of these two. Okay, I'm going to show you 2 ways to do it, basically corresponding to the two ways of writing the expression. But there are also slightly different ways of thinking about it. So here's the first version of the convolution sum. The y of n is the sum over all values of k of x of k times h of n minus k. And so this we can think of as an inner product, right? It's taking 2 vectors, multiplying them together pointwise, and then summing up the pointwise multiplication of the 2 points, which is, in 3 dimensions, it's taking the inner product between 2 vectors, finding how close to parallel they are, or whatever. Dot product, right? But what we're taking the inner product between is x of k. So, to take a dot product, we've got to have this dummy variable that we're summing over, this time axis that we're summing over. So that's the k-axis. So we take the k-axis, we write out x on the k-axis, but the h thing we modify before we put it on the k-axis. We reverse it in time, which is the minus k, and we shift it by n. So we're just moving it up and down the time axis. And then n is the particular value of y that we're trying to calculate. So to get each individual value of y, we take a time-reversed and shifted version of h, shifted by an amount corresponding to which version of y we want to calculate. Then we just take the inner product against our x, which is the same for every n. So that's what I've got here. Here's my x of k. So now this axis is k. X of k is 0, 3, 1, 2, minus 1. And here are different values of h of n minus k for different values of n. So this is h of n minus k for n equals 0. So h of 0 minus k, which is just h of negative k. It's the time-reversed version of h. Remember, h was 3, 2, 1. So now it's 3, 2, 1 going leftward. And to figure out the time shift when you do negative, when you're dealing, it's a little bit difficult to figure out exactly what the time shift is going to be here. But if we call this h of negative n equal to g of n, then we've got, I'll talk about that in a second. Okay, so here's h of n minus k for n equals 0, which is just h of minus k. And so to calculate y of 0, this first point, we take the inner product between h of k and x of k and h of n minus k for n equals 0. And so inner product is pointwise multiplication. So we have 0 plus 0, 0 times 0 plus 0 times 1 plus 0 times 2 plus 0 times 3 plus 3 times 0 plus 1 times 0 plus 2 times 0 plus 1 minus 1 times 0 plus 0 times 0. Turns out that there are no values of k for which one of these is not 0. And so the inner product between these two is 0. And so we do that calculation, we get that 0, and this gives us the y of n for n equals 0, which is the first output. Now, for n equal 1, we want h of 1 minus k, and this is where we get into this, like, which way do we delay this to make it h of 1 minus k. It's clearly going to be h of minus k with some shift, but we have to get the delay right. To get this right, we want to define g of n as h of minus n. Then h of 1 minus k is g of k minus 1. So this was g of k. So g of k minus 1 is delaying g of k by 1. And so we're actually shifting it this way, right? Because otherwise it looks like, well, maybe we've got a positive n0 in here, so maybe we're shifting it this way. But it's not, because it's a positive n0 compared to a negative time axis. So here's g of k minus 1. So we should take this whole thing, shift it over by 1, redo our point-for-point multiplication. Now, here's the non-zero range of g of k. Here's the non-zero range of x of n. We shift this over by 1, and now there's an overlap of 1 point in the non-zero ranges. So we get 0 times something, 0 times something, 0 times something, 3 times 3, something times 0, something times 0, something times 0. So now there's just 1 point of overlap, but 3 times 3 gives us 9, and so we get an output point here. Y of 1 is the inner product between these two vectors, which is 9 points, 9, value of 9. Okay, n of 2, again, we're going to do the same thing, but now we're shifting this over by 2 points, so now we have this h of 2 minus k, which looks like this. We do the same thing, and now we have 2 points of overlap between two sequences, 3 times 2 plus 1 times 3, which again gives us 9 here. And now we can see how this is going to work. So now we shift this over again, and we get 3 times 1 plus 1 times 2 plus 2 times 3, which is 11, which gives us this value here, and so on. So we can work this forward. And eventually, the last non-zero point is when this 3 is lined up with this minus 1 here, these 3 points, which is actually minus 1 times 1, which gives us the minus 1 last point here. And then after that, this thing is always in the 0 region. So again, the result is 0 for all values of n. So basically now we have calculated the output of the convolution here. I mean, I skipped a couple of points. But the output y of n, if this is the input x of k, and this is the input x, and this is our output h, which as we defined in the previous slide, we get this thing 0, 9, 9, 11, 2, 0, minus 1, and then 0 for everything else. So that was calculating the convolution, which we could have done by building that thing with the delays and just feeding in the sequence and letting the delays calculate it for us, and we would have got the same output. The point of this interpretation is that every output point here is this inner product. And inner products have some sort of, interpretation that in some sense they're a measure of how similar two signals are, right? I mean, they're not. The dot product of two vectors is the product of their lengths multiplied by the cosine of the angle in between them. So if they're parallel, then it's just the product of their lengths, the square root of the product of their lengths. Is that right? Yeah. And so this is interesting. If we have an impulse response that, when time reversed, looks like our input, then we'd expect to get large values coming out of the convolution. And to the extent that it doesn't look so much like the input, then we don't. We haven't learned anything over this expression by going through this exercise. We're still going to get the same answer. The point of this is intuition, that you can just work it through and get an answer. But now you can sort of have an understanding of what each individual part of that answer means. It means that there was some shifts here where these two things lined up. And that has a number of useful benefits, including being able to spot when you've made a mistake quickly. Because if the thing you calculate doesn't make sense with what your intuition is expecting, then you maybe want to go back and look to see why. So that was one way of thinking about it. Here's a second way of thinking about it. And actually there are more than two, but two is good to start with. And we're going to sort of drive this by using the other form of the convolution sum here. So now instead of having x of k times h of n minus k, we're going to have h of k times x of n minus k. And rather than thinking about individual points of y, we're going to think about this as an expression involving entire sequences. Entire sequences x of n minus k for different values of k. And so x of n minus k of different values of k is x of n delayed by different amounts. And we're going to have all these x of n's delayed by different amounts, and we're going to scale each one of them by a single value from the impulse response. So this is thinking about convolution as a set of scaled and delayed or shifted versions of the input where the scaling constants come from the impulse response. So here's x of n minus 1, x of n minus 2. Here are h of k. Now, the reason that we're interested in these particular values of these particular instances of shifted values of x is because h of k is only non-zero for k equals 0, 1, or 2. So we're only interested in, the only ones that are going to be non-zero are x of n minus k for k equals 0, 1, and 2. So x of n and its two delays. And then we're going to take x of n minus 0 and scale it by h0. We're going to take x of n minus 1, delayed by 1 point, scale it by h1. X of n minus 2, delayed by 2 points, scale it by h2. And so then it's like we take this entire sequence and multiply it by 3, this entire sequence multiply it by 2, this entire sequence multiply it by 1, and then we just sum them up. That's what we're saying. We're summing up over all these sequences to get the answer. So it's 3 times 3 plus 0 plus 0, which gives us the 9. 3 times 1 plus 2 times 3 plus 0 gives us the 9. 3 by 2 plus 2 by 1 plus 1 by 3 gives us the 11. 3 by minus 1 plus 2 by 2. It's minus 3 plus 4 is plus 1. It's plus 1 times 1 gives us a 2 here. 3 by 0 plus 2 by minus 1 plus 1 by 2. These two cancel out to give us a 0 here. And then 3 by 0 plus 2 by 0 plus 1 by minus 1 gives us the minus 1 here. All right, so this is just the summation of these three scaled, delayed versions of x. So we get the same answer, right? 9, 9, 11, 2, 0, minus 1. Because it's the same calculation we're working out. Basically, all we did was we noticed that sometimes we were, doing the same numbers because it's giving the same answer. But we're thinking about where those numbers come from in a very different way. We're now thinking of it as these delayed and shifted versions of x, rather than before we were thinking about inner products with time-reversed and shifted versions of h. And so depending on the structure of x and h and their relationship, this might be a more simple way to quickly get an intuitive expectation of what the output of a convolution is going to look like. So again, it's the same thing. It's an intuition which gives you a quick, rough idea of an answer against which you can check what you get, or if you're trying to design something, you can think, well, this is the kind of the feeling of what I want, so roughly speaking, this is the way I would want to do it. Any questions about those? I hope you see why I'm going through this. This is kind of the essence of what I want to achieve, which is to give you a sort of a deeper inner feeling for what these things are doing. Okay. While we're talking about interpretations of convolution, let me just mention this one, the matrix interpretation. Here's the convolution sum again. One of the places where we get this, inner product type operation, this sum at the pointwise product of two vectors, is in linear algebra. And in particular, this expression, if we think of y as a vector, so y of n as a vector, because it's a set of values of y for different values of n, like this, then we can calculate this expression as the product of a matrix here and h expressed as a vector. And so to get the right values of x, this matrix here is composed of different values of x. And they're moving backwards in time, right? Because it's the inner product of h considered forward in time and now x considered backward in time. And then for each successive value of y, the values of x shift over by 1 because y0 is, y0 is x of n minus 0 minus k for some values of k times h of k. So the only values of k we care about are k0 through 2 here. So it's x of x of 0 minus 0, x of 0 minus 1, x of 0 minus 2, times h of 0, h of 1, h of 2. That's what this matrix multiplication gives us. The first value here is the inner product of this row and this column. The second value is the inner product of this row and this column. So we end up with this particular matrix composed from x, but it's for as many points as we want here, it's the length of h times how many points we want as output as rows. And then we have this kind of diagonal structure where every row here is the previous row shifted over by one with a new point, successively larger n coming in from the left. This is called a Toeplitz matrix, and it has various nice properties in linear algebra which allow you to do clever things with this linear algebra expression of convolution. But that means that we can express convolution in linear algebra just by having an operator to generate this convolution matrix from our input signal. And of course, because of the symmetry, we could do this the other way around, right? We could have h's here and x's here. But in this case, h was finite, which made it nice because then I could have a finite number of columns here. If I tried to do it with x, then I would have ended up with, having to know how many non-zero values of x there were to choose how many versions of h to put in here. Okay, a few other notes about convolution. We saw that with these finite length sequences, there's always this sense that you're shifting one of the sequences and then taking in a product. So if you have two finite length sequences, meaning that there's 0 outside some range, then for a lot of the shifts, there are going to be no overlapping non-zero regions, so you're going to get 0. The only time you're going to get, so if we think about that version where we're taking h and then time reversing it and then shifting it along and taking the inner product, you're going to get 0 values until you get to a large enough shift that the first points here overlap. And then you're going to get successively different values until the last points overlap, and then it's going to disappear. So the total number of times it'll overlap, like if the one was shorter than the other, the total number of times they overlap is the length of this one plus the length of this one minus 1, right? Because the first time they'll overlap here is when this one hits the first point, when this one hits the first point. If you think about it, you'll see that this is correct. So this is the outcome. If you convolve a length n sequence with a length m sequence, both finite length sequences, the total number of output points is n plus m minus 1. Okay. Obviously, we've written this convolution sum in this consistent way. We're using this convention as y as output, x as input, h as the impulse response, and k as the summation variable that we use to calculate the inner product. We could have used different symbols, and in general, you will come across situations where there are different symbols in here. But if you can spot this pattern, then you can say, oh, wait, that's just a convolution of these two. But the key thing to look out for is this situation where you're taking two vectors, but you're reading one of them in one sense and the other in the reverse sense. So you have an index variable here. You're reading h forwards, but you're reading x backwards with some shift. And so the thing is, in this situation, when you sum up these two indices, just as a kind of mnemonic, you sum up the two indices, and the k disappears, and you just get the n, the actual output index coming through. So this is just a, if you're confused, it's a quick trick to spot that this is a convolution and not, for instance, a correlation, which we'll talk about in a little bit. Convolution, as I'm trying to stress, is a very basic, very important operation, and as you would expect, it has its own primitive in MATLAB, because it's something you actually want to be able to do, so something you might want to calculate in MATLAB. So conv implements convolution. You give it two sequences, and it calculates the output. So if we define A as our input sequence here that we had from our example, and B as our impulse response, then conv AB gives us this output sequence. Now, MATLAB, for reasons of efficiency or, because of the way it is, it's very happy. It only can deal with finite length sequences, in fact, right? Because it's only got finite amounts of memory. So every sequence is a finite length sequence like this. And so when you do convolution, it gives you a finite length sequence out. And MATLAB doesn't say where time 0 has to be. In most cases, you can work by assuming that time 0 is the first point. And then it gives you this convolution as output, where in fact this is the output at time 0, and these are successive times. It gives you a finite length output because, of course, with a 5-point input and a 3-point input, the total number of non-zero points is going to be 5 plus 3 minus 1, 7 points, which is what we get here. So, you can interpret this as saying, well, here it's a sequence starting at 0 with every other point equal to 0, but MATLAB doesn't have to even force that interpretation on you. It's saying, well, if you give me two finite length sequences, I can give you the output of the convolution, and it's going to be this finite length thing. So let's just look at this in MATLAB briefly. So again, we've got the we've got the script here that does this, and in fact, we can rather than calling them A and B, we can call them X and H as we did. And we can plot the results. Let me just do that much. Okay, so here's, so now if we have X like this, 0, 3, 1, 2, minus 1, and H, 3, 2, 1, then conv X, H gives us our 0, 9, 9, 11, 2, 0, minus 1. We can plot all of those here. So here's 0, 3, 1, 2, minus 1. Here's 3, 2, 1. MATLAB because of its Fortran heritage, it likes to refer to the first element of a vector as index 1 rather than index 0. So it's plotting these against 1 to 5 rather than 0 to 4, and 1 to 3 rather than 0 to 2. That's just annoying. There it is. And then here's the convolution, 0, 9, 9, 11, 1, 0, minus 1, whatever it was. And again, it's plotted them as 1 against 1 to 7. Obviously, we can get it to plot differently just by saying it to plot 0 to 6 against X. 0 to 7, not X. Y. There you go. Or even stem. Right, so then you can tell it what numbers to write down here, but by default, it assumes 1, starting from 1. Okay, so that's no problem. We can easily define and operate on convolution with MATLAB. So that was conv xh. Just to check, of course, if we put them in the opposite order, conv hx, we get the same values out. That's what we're saying, that the argument order doesn't matter in convolution. So let's just check that that works okay. And it does. So here's something interesting. I said that convolution is what linear systems do. I also said last time that the acoustic system in a room or in any kind of sound system is actually very well matched by a linear time invariant system. The sound, basically, sound is these pressure waves in the ambient air pressure, but the ambient air pressure is very large, and compared to the small deviations, actually really very small deviations that sound generates, it's basically linear, right? You're taking maybe it might be a large-scale nonlinear thing. These little deviations, it's pretty linear. And, in sort of more or less stationary conditions like this, these things don't change very much. So what that means is, if you want to predict what the sound of, say, me speaking to some point in the room is going to be, you could take a recording of me speaking from a close mic just right here by my mouth. You could measure an impulse response from where my mouth was to some point in the room, and you could do that by generating an acoustic impulse, which is classically done by using a starter gun, starter pistol, or maybe bursting a balloon, something that generates a very, very sharp crack. And then just recording that impulse response. And then you can convolve the two, and you get something which would sound like if I'd been speaking in that room. So, and you can really do this, and it's kind of an amazing effect. So here is some speech.
The football team coach has a watch thin as a dime.
And here is an impulse response, which I actually recorded myself. Is that what it's called? Yes. I just went into the concrete stairwell of the building where I was working at the time, and I actually just clapped. It was not a very clean impulse, but you can hear that it sounds like you'd expect it to hear if you clapped in a very acoustically live concrete stairwell. So let's just see if we can hear that. It's kind of short, but you can hear the sort of, it sounds like someone slamming a door or something like that. And so the assertion is that if you convolve those two, then it's what it would sound like if I'd recorded at the same distance, but instead of clapping, I'd spoken. And so we can do y is conv of h and d. So let's just remind ourselves that d is this vector of 49,000 points because it's 3 seconds or 16,000 samples per second. H is 12,000 points, so it's a little bit under a second, like 3/4 of a second of that little impulse. And so when we convolve the two, we get something which is what? 51 something, yeah. Oh, 61,000, yes, thank you. 61,000. Don't even add. It's 49 plus 12 minus 1. Okay. So if we listen to that.
The football team coach has a watch thin as a dime.
Just compare it to the original again so you can hear the difference.
The football team coach has a watch thin as a dime. The football team coach has a watch thin as a dime.
So I hope you can hear that sounds like a pretty good, sounds like a very plausible recording of someone speaking in a very live acoustic environment, because that's really all it is. This is a real good simulation. Yeah.
Is that how your music software add reverb?
Yeah, absolutely. So in recording studios, you often want to add reverberation. Reverb is an amazing thing. So reverb is that sound, which is basically reflections coming off the walls, but there are so many and they get very, very dense. And for reasons which are not at all obvious, and I can't explain, some kinds of music, they just sound much nicer with reverb added, particularly vocals. That's why, people classically sing in the bathroom, because the sort of reverberation in the bathroom makes it sound better. And so there's a big need when you're making recording music to try and simulate that effect, but you don't want to have to go out and hire some big concert hall. To get a really nice reverb, typically you need a large concert hall. And there's this huge history of architecture of how to build these concert halls that sound good. It's like you might build a concert hall to sort of just try and accommodate people, but if you get it wrong, it can sound terrible. And if you get it right, there were various concert halls which, through history, through hundreds of years, people said, I really like the way it sounds in that place, and it was because of the particular reverb. So rather than having a concert hall, you'd like a box where you could just feed the microphone in and get it to sound like that. And so these are artificial reverb. And now, as of initially, that kind of convolution would have taken, days to do on a 1970s computer. And so they had better ways of doing it. Now we can run it pretty much in real time. So as of around 1990-something, they started having these direct convolution reverberation units, which could then simulate a particular room. You could go into some concert hall, you could record its impulse response, you could say, okay, press this button for the Albert Hall, this button for, the Boston Symphony Hall. And that's how I do it, yeah.
So I'm surprised, so we left the sample rate constant, but now we have more samples.
Yeah.
But there was no change in tension.
Right. No, there was change in length, right? We started off with 49,000 samples, we ended up with 61,000. Before we'd gone this whole thing about samples and time and sample rate. Here, basically, almost all the time when you're dealing with stuff, you hold the sample rate constant and everything works properly. So what happened here was we took this, let me just plot these. How am I going to do this? again, I'm getting a little bit, MATLAB's not doing exactly what I want, but if I plot D, right, so this is the sound, this is the dry speech. And then I can plot H, this is the impulse response, and then I can plot Y, which is the output. Now, these things all look the same, but actually they've got different time axes here, because they're all different lengths, as we know. If I link axes, yeah, there you go. If I link axes, then MATLAB tries to use the same axes for each of these things. And so here's the long one, which is 61,000 points long. This is 10 to the 4 and 6, so 60,000 odd points. Here's the input speech, which is 49,000 points, and here's the impulse response. You see how it dies away. That's basically, there's the energy at the beginning, gets reflected around, but then it loses energy all the time, so it dies away like this. And that's like, whatever it is, 12,000 points long. And so this length here is basically this length plus this length minus 1 point, which we can't see here. And so what happened is, this is in samples. I could have, if I divide by 16,000, I get time here. So here, this is the 3-second mark. And what happened is, this is now 4 seconds long, right? So what happened was, because like if I put just a single impulse in, which lasts almost no time, then the sound coming out of that is now, the impulse response long. When the impulse response extends out the input signal by however long it is. That's why if I have an n-point input and an m-point impulse response, the output is n plus m minus 1 points long. It's been extended out by those m points of the impulse response. So that's what happened here. It's longer, but it took longer to listen to, which is why everything sounds the same. And that's normally how it works. The idea that we could have sped this up to make it last the same out, but that would have been a kind of strange and perverse thing to do. So that we only do that in lecture 1. So that sort of hopefully explains what's going on there. Yeah.
Is this only a digital process?
No. Is this only a digital process? No. So convolution is, like I say, it's not what discrete time linear shift invariant systems do. It's what linear shift invariant systems do. When I'm speaking to you, that's an analog thing, right? I'm actually making real pressure, and it's propagating out. So that's kind of even weirder, right? We've written, well, it's not that weird. In continuous time, the summation becomes an integral. Basically, you write it the same way, and it all works out. So the y of t is equal to the integral of x of t, h of n minus h of, integral of x of tau, h of t minus tau over tau. And it's the same. It's just, it's like sampling on a very fine grid. But, perhaps then the idea that a physical system is actually implementing that integral is kind of slightly weird. It's like, okay, that's an interesting way of describing what a physical system actually does. But yeah. Yeah.
Let's say that we know the outputs and the impulse response. Can we get the inputs?
Yeah, that's a great question. So if what we've been doing here is we're taking the input and the impulse response and we're looking at the output. But what if we knew the output, we knew the impulse response, so we knew what the system is doing, can we get back to the input? And the answer is sometimes, that certainly you'd think that you'd be able to, because you've got enough information there. It's like if we write convolution as y equals h convolved with x, then if I tell you 2 of those things, your intuition is you should be able to work out the third. It turns out the reason we'll talk about that. Maybe we'll talk about that now. Let me just see what the next slide is. But that's called deconvolution, right? Or inverse convolution, and it's an interesting problem which we'll talk about. Oh, come on. Okay. You can do it except in the case where maybe the system is removing some information. So if the impulse response was 0, then obviously you wouldn't be able to do it. There'd be some kind of divide by 0 you'd come up against. And there are also interesting problems of stability that, depending on if you do it like algebraically, you end up with errors accumulating. But there's a slide on this later on. If you just hold on. Yes. Right. So this, if you think about it as a matrix operation, if we know y, well, the way we do it is we'd have, if we're trying to recover x and we knew y and h, then we could write this as this part would be h based, and this part would be x based, and then we'd say, well, if y equals hx, then x should equal h to the minus 1y, but it's not square, so you can't do it. But you can do a least squares solution. It's the normal equation. So you have the pseudo-inverse here, but again, that's not guaranteed to be invertible. You could still get a singular one there. Yeah?
Can we compute the inverse of h and convolve y and h?
Yes, we can compute the inverse of h, but we have to figure out what that means to do. It's coming up. It's coming up soon. Thank you. Okay. So yeah, here we go. It's just one slide away. So hang on for a second. Okay. So we've got this idea of convolution as what happens to a signal when it goes through a system. And the system could be, some box, or it could be some physical system like the room. You can take that signal and you can put it through another system, right? You can continue to do things to it. And then you can think about those two systems together as a single system, and you've got an overall response. If you have two systems get together like this, again, I'm defining them by their impulse responses. This has got an impulse response of h1, this has got an impulse response of h2. Then clearly, if I have x here I have x convolved with h1, and then here I have x convolved with h1, convolved with h2. But we had the associativity of convolutions. That's the same as taking x and convolving it with the convolution of the two impulse responses here. All right, that just sort of comes out of the algebra, but it's kind of interesting that we can summarize the net result of multiple systems just by combining their impulse responses through convolution. Another thing we had in the algebra was that if we convolve with h1 and then if we have something which is the result of convolving h1 and h2, it doesn't matter which order we applied h1 and h2 in. So if we have two systems and they're both linear shift invariant, then at least ideally the output doesn't depend on which order we apply them. We can move them around in sequence and we get the same output. This is just taking the algebra and drawing it into blocks, basically. Okay, so this question of inverse systems. Delta of n, let's just make sure that we've noted this. If the impulse response itself is delta of n, that means I put an impulse in and I got an impulse out, which means that it didn't do anything. It's the identity system, which is to say that x of n convolved with delta of n is equal to x of n. So delta is the identity. Now here's this system here's this problem we're talking about. We've got an input x of n. We put it through some system. We got y of n, the output, but maybe we don't have x of n. We're going to put it through a second system to get a second output, z of n. And let's say we wanted to try and recover x of n because we couldn't access it. Can we do that? Well, z of n is just h2 of n convolved with y of n. Y of n was just h1 of n convolved with x of n. So it's h2 of n convolved with h1 of n convolved with x of n. If this part, h2 of n convolved with h1 of n, gives us a delta, then this would be delta convolved with x of n, so it would just be x of n. And in that case, what we'd have is a way of recovering x of n from y of n. So we'd say we have a way of undoing the effect of h1 of n. So we'd say that h2 of n is the inverse system of h1 of n, because we can get from x, we can get the output, the result of applying h1 of n, we can undo it and recover x of n back out. So this is just like, we haven't said anything about how to do it now, this is just the terminology of what we're going to do. So then the question is, can we find this h2 of n for a given h1 of n? If we could use it to recover the output it's clearly not going to work in all cases because there are situations where basically h1 of n removes information. Obviously, if it's identically equal to 0, then y of n is identically equal to 0. There's no way you can recover anything from x from that because it's just disappeared. But it turns out there's a broader set of cases where something like that happens, where some of the information is lost. But basically, all we have to do is try and solve this expression here, where we can write down the convolution sum, the h1 of n's, which we know, the h2 of n's, which are the things we're trying to find, and we write them out in this equation to get delta of n and just solve for it. This is just, you could think of this as a large simultaneous equation, although it turns out one of the things that's going to show up is that h1 of n may be finite length, but h2 of n is not going to be finite length, except unless you're lucky. But you can still, do your best to solve it. Let's just show that there's one that exists, so we know it can happen. The accumulator, remember the accumulator was the thing that had the delay and then feedback into the sum, and so the output was just the sum. The output wire was a sum from L equal minus infinity through to n of x of n. If you think about what happened, we know what happened when we put an impulse into that. We can figure out what happens. It's 0 until time 0, then the impulse goes in, and then after that the impulse keeps looping around. So the impulse response of the accumulator is just the step function, mu of n, right? It's 0 for n less than 0, and it's 1 for n greater than or equal to 0. Now, if we have a system whose impulse response is like this, you put an impulse in, you get a 1 out, then you get a -1 the time afterwards, and then 0 from there on, which is just a straight through and then a delay with a negative sign coming out, right? That's what would give you this. This is it's like the three-step thing with alpha 1 equal to 1, alpha 2 equal to -1, alpha 3 equal to 0. If we convolve this with this, then think about it in terms of the delayed versions of x scaled by the corresponding values of h. So the value of h0 is 1. The value of h1 is -1. So if we convolve mu with that, we get +1 times mu not delayed, -1 times mu delayed by 1, and then we sum them up. And so here all of these points cancel out, and we're just left with the 1 at time 1. And so yes, the convolution of mu of n and delta of n minus delta of n minus 1 is delta, which means that this system here, which you can call a backwards difference, taking the difference of two successive points, right? Well, we can build that very easily. That's the inverse system for the accumulator. So you can build the accumulator, it's a real thing. You can build this, it's a very simple thing. And if you've got the output of a signal that's been put through an accumulator, you can put it through this to recover the system. Basically, it's just, integrating and then differentiating, something like that, to recover it all. And of course, there are a lot of different versions, but that's at least the simplest one that we can show. So we can find one real case of an inverse system pair. So it does actually, it is real. It does mean something. Okay, let's just do this one last slide so we get this out of the way. One of the other things we saw with the algebra was that convolution was distributive over addition, which means that if I had h1 plus h2 convolve with x, it's the same as h1 convolve with x plus h2 convolve with x. And so here's that written in block terms. It's saying if we have two systems, we feed them the same input and then add their outputs together, we can collapse that down to a single system whose impulse response is the sum of the two impulse responses. So in this parallel connection is sort of like a linear superposition of two different impulse responses. And then next time we'll talk about these linear constant coefficient difference equations, which are kind of like the general solution. Any questions about this before we go on? All right, great. I'll see you on Wednesday.